Hi folks, welcome to our introduction to logarithms, which is in R7. There's four main things that we need to cover in R7, and they're listed there for you. So explain the relationship between logarithms and exponents, express a logarithmic expression as an exponential expression, and vice versa, so you have to go both ways. Number 3, determine without technology, notice the crossing out of the calculator over here, the exact value of a logarithm. And then very similar to that one, we have estimate the value of a logarithm using benchmarks and explain the reasoning. So we're going to start off with just a little bit of review, and that is just talking about exponential functions, which is our first piece here, exponentials. An exponential function is something that has an exponent. So y equals a to the power x is our exponential function, where a is the base and x is the exponent. And these aren't quite exponential functions, but they are exponential expressions. And we're just going to evaluate a few just to get a reminder of how exponentials work. So 2 to the power 1 is just a 2. 2 squared, well, that's 2 times 2. So that is 4. 2 cubed is 2 times 2 times 2, so 2, 4, 8. And so each time we move up on our list, because our powers are increasing by 1, we're multiplying by 2 one more time. So 4 2s is 16, and 5 2s is 32. So every time we move up, we multiply by 2. What happens when we go down on our list? We go 32 and we go down 1. Well, we divide by 2. And let's go down once more. Again, we're dividing by 2. So each time we are dividing by 2. And that pattern continues, which is why when we go here and we divide by 2 again, 2 divided by 2 is 1. So that's why anything to the power 0 is 1. And then we'll do the same thing here. So we're going to divide by 2. 1 divided by 2 is 1/2. You know I'm not much of a decimal guy, so I'll use the fraction there, 1 over 2. And then we just keep this pattern going. So 1 over 2 squared, I could write it like that, or more simply 1 over 4. And then our last one, again, we're going to divide by 2, so that's 1 over 2 cubed, or more simply put, 1 over 8. So just a quick little rundown of exponents. Now we have some rational exponents over here, and rational means fractions. So when you have a fraction here, that generally means we're going to introduce a radical. So 2 to the power 1/2 is the square root of 2. So you'll notice that the denominator ends up as the index of the radical. We don't write the 2 there because it's just assumed to be 2 if there's nothing there. But for this one, the 5, because it's in the denominator, is going to become the index, and then x is underneath the radical, and the 2 stays as the exponent to the x. So the denominator becomes the index, and the numerator stays underneath the radical. So just to solidify that, c as the denominator is going to become the index, and then a stays there, and it's to the exponent b. So here we're going to solve for the variable in a few situations. Starts off pretty easy. So y equals 2 cubed, which is 2 times 2 times 2. So we have y equals 8. Feel free to pause the video at any point if you want to try it before it comes to be my turn. So y equals 3 to the power 4. So that means we have 4 3s. And some of you maybe know the answer already, but I would do it kind of step by step. 3 times 3 is 9. And then this is also 3 times 3, so that is also 9. And 9 times 9 is 81. Here we have one that's a little bit different. Rather than having our variable by itself, now the variable is part of an exponential expression. So this can be a little bit trickier to solve. But what we can do is we can hopefully express this as a base of 2. So if we go 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So there's 1, 2, 3, 4, 5, 6 2's. So 2 to the power 6 is equal to 2 to the power x. Now, if our bases are the same, the exponents must also be the same. So our variable is equal to 6 in this case. Feel free to pause the video before I do this next one. So same process as we just used. We want to express this 27 with a base of 3. So 3 times 3 is 9, times 3 is 27. Okay, so that is 3 3's. So the bases are the same, which means the exponents must be the same, and x is equal to 3. Now for our next one here, very similar as this one. We're only off by 1. So you'll notice that we use 6 to get to 64. If we were to do one more, that gets us to 128. So there's no way we can express this as 2 to the power. We know that it's more than 6, but not quite as many as 7. So without a calculator, we can't really guess that it's 6.1 approximately. So that's not good enough because we want to solve it. So what we need is actually a logarithm. And logarithms are the inverses of exponentials. So if we have an inverse process, we can end up solving for this x here. So if I were you, I would highlight this logarithms are inverses of exponentials. And when we sketch an inverse function, when we're given a parent function, you're going to switch the x and y coordinates. So the coordinate xy ends up being yx. Or to give you specific numbers, if we have negative 2, 5 as the coordinate on a function of f of x, so this is on f of x, if I want a point on f inverse of x, I need to swap these coordinates. So it'll be 5, negative 2. So if this is the coordinate on f of x, this is our coordinate on the inverse of x. And then we're going to give you some examples of inverse functions. So again, to find the inverse, we switch x and y. So we're going to say x is equal to y plus 2. And then we want to isolate for y. So we're going to subtract 2 from both sides. X minus 2 equals y. So you'll notice that my original is x plus 2. The inverse is x minus 2. So addition and subtraction are inverse operations. Also, this is the inverse of that. Let's try this one here. So y equals 2 times x. If I want to find the inverse, I need to switch the x and y coordinates. So x equals 2y. But I want to get y by itself. So I'm going to divide both sides by 2. So I get x over 2 equals y. So this is the inverse of the original up there. In the original, I had 2 times x, or x times 2. Over here, I have x divided by 2. So now we have multiplication and division being our inverse operations. Kind of like the opposites. Now our last one, we have an exponential function. So y equals 2 to the power x. Again, let's switch x and y. So x equals 2 to the power y. And up until this point in time, we don't really have a way to move this 2 over. But that is exactly what a logarithm is. A logarithm is a way to isolate for the exponent. So what's going to happen is this 2 moves to the other side, but it becomes log subscript 2 of x. So I'm going to put the x in brackets here, but it won't always be in brackets, whatever the logarithm is acting on. And then your y, which was a superscript, is just a regular y now. So logs and exponents are inverses of each other. If you switch x and y, you'll be able to flip them and solve using our logarithm. So we're going to practice writing exponential equations in logarithmic form. So what happened up here is we took the base and we moved it to the other side as part of the logarithm. So I'm going to move the base to the other side. So we have log base 2, and this x, which was here, just stays right there. So log base 2 is acting on the y. And then the exponent ended up just by itself. So my exponent here is 3. So the 2 switches down to the other side. Feel free to pause the video and try the next one on your own if you're comfortable doing that. So to put this in logarithmic form, we're going to do the same thing. This 3 has to move over to the other side. So we have log base 3 of 27. Again, these brackets are optional, but you can put them there if you like. I didn't put them in the first one around the y, but I could have. And then the exponent ends up right there. And now we have our last one. Again, the base is going to move to the other side. So log base 10 of 10,000 equals 4. Now, just like we went from exponential form to logarithmic form, we could also go logarithmic form to exponential form. So going exponential to logarithmic, the base moves over to become the base of the logarithm. So if we were to undo that, this 2 has to move back to the other side. So now the base of the logarithm has to move to the other side, and what was by itself is going to have to become the exponent. So x is the only thing that doesn't change. We have x equals, now this 2 is going to become the base to the exponent 5. Feel free to pause the video before each of the next 2 examples if you want to try it on your own. So the base of the logarithm is going to move to the other side. So 16 equals x to the power 2. Same thing over here. Move the x over. 27 equals 3 to the power x. Two more things I want to go through. First of all, we're going to determine the exact value of each logarithm. So to just look at these by themselves, at least at the start, it's tough to see what they actually are. So I would encourage you, if you get something like this, to make it equal something. I like x. So log base 2 of 16 is equal to x. So to solve this, I would put this into exponential form. So this 2 needs to go to the other side. So 16 equals 2 to the power x. We think all the way back to here. This is a very similar question that we solved. We had some number equals some exponential. So we want to express this number with a base of the other side. So we want to express 16 with a base of 2. So 16 is 2 to the power 2, 4, 8, 16, so 4. Then because the bases are the same, the exponents must also be the same. So this logarithm is equal to 4. Again, feel free to pause the video before each of these examples if you want to try it on your own. So I'm going to start out by setting this equal to x. Then I'm going to write it in exponential form, so the 5 moves over to the other side. So 125 equals 5 to the power x. Then we want to do the same thing. We want to express this with a base of 5. So 5, 25, 125. That is 5 cubed. So the bases are the same. That means the exponents must also be the same. The third one, I'm going to do the exact same process. So I'm going to set this equal to x. Now the 7 has to go to the other side. And this should actually be a 49 in here. So set that equal to x. And 49 equals 7 to the power x. So we have to express 49 with a base of 7. So 49 is 7 squared. Now that our bases are the same, our exponents must also be the same. Now this last one is the most tricky because we have a fraction. But the process remains the exact same. The base moves to the other side, so 1/8 equals 2 to the power x. Now the tricky part is figuring out how 1/8 can be expressed as 2 to the power something. Now I'm going to scroll way back up near the top here, and each time we move down, we divide it by 2 in our list here. So 2, 1, 1/2, 1/4, 1/8. Because 8 is 2 to the power 3, and a negative exponent just takes the reciprocal, so 2 to the power negative 3 is the same as 1/8. So we can express this as 2 to the power negative 3 is 2 to the power x. And because the bases are the same, the exponents must also be the same if our equal sign is true. Last thing here. Estimate the value of each logarithm to 1 decimal place. So we could try doing the same process we just did. So we're going to move that 3 to the other side. So 8 equals 3 to the power x. But you might remember that by powers of 3, we have 3, and then 3 times 3 is 9, and 3 times 9 is 27. We're already way higher than 8. So 3 is 3 to the power 1, 9 is 3 to the power 2, 27 is 3 to the power 3. We're obviously not going to get an integer for x. So the word estimate here lets us know that we don't need to use a calculator. Also, at the start of the video, we said we don't get a calculator on this one. So we're going to have to take a guess or use benchmarks, which is what these are, to make a guess at what x is going to be. So we know it's going to be more than 1. It has to be less than 2 because we're less than 9, but we're not less by very much. So we're going to say that x is approximately equal to, and something that's closer to 2 than it is to 1. So I'll say just a random guess of 2.8. So this is creating the benchmarks, and then I make my estimate off of that. Let's do the next one. Again, we want to put this in exponential form. 100 equals 5 to the power x. So let's look at our powers of 5. We have 5. 5 times 5 is 25. Times 5 again is 125. And now 100 fits right in here, right? It's between 25 and 125. So 5 is 5 to the power 1. 25 is 5 to the power 2. 125 is 5 to the power 3. So if this is where 100 is, 100 must be between 2 and 3. Now 100 is closer to 125 than it is to 25, so it's going to be more than 2.5. And all I'm really looking for is that you're getting on the right side of that halfway mark. So I'm going to say that x is approximately equal to 2.7. Yeah, as long as you're higher than 5, it's probably higher than 6. But I don't have a calculator because I don't get one, so I don't know for sure. Feel free to pause the video and try these next two on your own. So let's set this equal to x, put it into exponential form. So 90 equals 2 power x. Now we need to set some benchmarks for 2. So we have 2, which is 2 to the power 1. And then we have 4, which is 2 squared. And we have 8, which is 2 cubed. And we have 16, which is 2 to the power 4. And we have 32, which is 2 to the power 5. We have 64, which is 2 to the power 6. And then we have 128, which is 2 to the power 7. So 90 falls between 64 and 128. So that means our answer has to be between 6 and 7. So this one is pretty close to being right in the middle of 64. Maybe just shy of that. Sorry, just shy of the halfway point between these two. So I'm going to say that, so we're at 6, and we're pretty close to halfway, so I'm just going to call it 5. And now let's try the last one. So set this equal to x. 9,612 is equal to 10 to the power x. Now I'm going to do this next part vertically because I just have the space. So my powers of 10 are 10, 100, 1,000, 10,000. Okay, so 9,612 would fit in there somewhere. So this is 10 to the power 1. This is 10 to the power 2. This is 10 to the power 3. And 10 to the power 4. So our exponent, our value for x, is going to be more than 3, but less than 4. 9,612 is much closer to 10,000 than it is to 1,000. So we want to have a number that's much closer to 4 than it is to 3. So x is approximately equal to 3.9, we'll say.